Okay, in this video I'm going to be working some more problems for linear algebra that, go around the idea of basis and dimension. And so this is probably, for you, Classwork 5.2 solutions. Well, maybe you're just interested in more example problems for basis and dimension for high school linear algebra. So the first one starts with a matrix A, which is, I'm just going to copy it real quick, 2, 1, 2, negative 1, 4, 2, and 1, negative 1, 1. Okay. Oh, and then it says, okay, I thought this was one where we're going to need to reduce. Oh, interesting. Yeah, this is a good problem because it's getting towards the eigenvalue problem, which is kind of where we're headed after this unit. And, well, W equals the set of all vectors in R3 for which, if I multiply them by A on the left, it's the same as taking the vector and scaling it up by 3 times. Okay, that's an interesting scenario that we'll be interested in soon. Okay, first part is show that W is a subspace. Well, I'm just going to show that it meets the 3 conditions. Okay, the 0 vector needs to be in it. Okay, is A times 0 equals 0? I know that. For any A, if I take A and I multiply it by the 0 vector, I'm going to get the 0 vector back. A0 equals 0, which also happens to be 3 times the 0 vector, so good. Okay. For addition, suppose I've got X and Y are in W. Okay, that means that AX equals 3X and also AY equals 3Y. Okay. So if I'm going to see what happens when I take A and I multiply it by X plus Y, am I going to get 3 times X plus Y? Well, we'll find out. I'm going to use the distributive property. That's AX plus AY. And that's equal to, well, AX is 3X. Oops, I didn't put the little hat on it, but it still is. 3X plus 3Y, which is, I've got enough room, that's 3 times X plus Y, which means that, okay, the space is closed under addition. It's closed under scalar multiplication is going to be, okay, so suppose X is in W and K is a real number. Let's see what happens to KX. Oh, okay, this is a property that we have that if I'm going to do matrix multiplication on a scalar multiple of a vector, I could do the multiplication of matrix vector and then scale it up afterwards. Okay, so that's K times AX. If X is in W, then that means AX equals 3X. So that's K times 3X. And, K is a constant, 3 is a constant. I could say that's 3 times KX. Okay. And that means that I have satisfied all 3 conditions showing that W is the subspace of R3. Okay. Now, for part B, I'm a little interested in this. Let's think about solutions to A minus 3IX equals 0. So where that comes from is AX equals 3X. Subtract 3X from both sides. Okay. If I wanted to factor out the X on the right, I can't really take A minus 3. It doesn't make sense to take a matrix minus a number. But the effect on X would be the exact same if I changed that 3 to a 3I. And then it would work. So that's why they're telling us to be interested in the solutions to that equation. Well, I can do A minus 3I. That's going to be 2 minus 3, 4 minus 3, 1 minus 3. Otherwise, everything will be the same. And negative 1. 4 minus 3 is not 2. That's going to be 1. Right, so that's going to be a 1 there, and then this will be a 2, 1, negative 1, and also 1 minus 3 is negative 2. Okay, so this thing looks very row reducible, right? This is going to go down to, really I'm going to have, or maybe I multiply this by negative 1, make everything positive. But, this is just a scalar version of that, and this is also a negative version of that. So I'm just going to end up with 1, 1, negative 1, 0, 0, 0, 0, 0, 0. Okay, and find a basis for W. Well, basis for W is the same as the null space of this matrix, right? Because I'm looking to find the null space of A minus 3i. So I'm going to go ahead and say, okay, I found it. x1 plus x2 minus 3x3 needs to equal 0 if I'm computing the null space. So x1 equals negative x2 plus x3. x2 can be whatever it wants. x3, going off the shot, but x3 can also be whatever it wants. Okay, so the vectors that comprise W are x equals x2 times negative 1, 1, 0, and x3 times 1, 0, 1. So that means that a basis for W is equal to the set that has negative 1, 1, 0, and 1, 0, 1 in it. That was a good problem. I like that one. If you liked that, then you'll like solving the eigenvalue problem. That was basically what we just did. Okay. Second one, B. Okay, I'm going to copy B. So B equals 1, 2, 1. Negative 1, 2, negative 1. 2, 5, 0. And 3, 4, 7. All right. If I reduce this, I'm going to get that matrix right there. And do a little bit of row reduction magic. And so that was, I think, the first part of the question. It was asking, yeah, reduce B to echelon form. Okay, that is echelon form. It's also reduced echelon form, so, you know, I'm just going to do that. Determine the rank and nullity of B. Okay, so that was part A. Part B is rank is going to equal the number of pivots. Nullity plus rank equals the total number of columns. So there's 4 columns, 3 of them are pivots or have pivots in them. And the nullity is going to be 1 because there's 1 left over. Okay. Then find a basis for range of B that consists of columns of B. It's going to be the first 3 columns of B. So 1, 2, 1, negative 1, 2, negative 1, and 2, 5, 0. I was worried. I was like, wait a second, this isn't linear independent, but I see that if that was a negative 2, then that'd be a different story. Okay, that's the basis they're asking for. Find a basis for the row space of B. Okay, it looks like all 3 of these, they're going to be independent, so I could use those 3 rows, or I could use these 3 rows. And so I'm going to say that's the basis, just the non-zero rows of the matrix in reduced form. Okay, find bases for the row space and column space of B transpose. I feel like there's a finesse technique I'm not seeing here. Well, this is going to be a basis for the column space of B transpose because the column space of B transpose is the row space of B. Okay, so the one for row space of B transpose, that would be, oh, yeah. That one. And basis for the range of B transpose is going to be that one. Because the row space of the transpose is the range of the original, and the range of the transpose is the row space of the original. So I've already done that. Yeah, that's the finesse way. Find a basis for the null space of B. Well, gladly. Okay. This augmented with 0 is going to give me the solutions to the equation Bx equals 0. So I'll have x1 minus or equals negative 7x4. I'll have x2 equals 0. x3 equals, hold on, x3 is going to be 2x4. I don't know why I was having trouble with that. x4 can be whatever it wants. So the null space, basis for the null space of B, is -7, 0, 2, 1. Okay, that'll be all for that one. Okay. Well, we'll find out. I'm not sure. I was trying to see if I could look at that and see combinations of V1, V2, and V3 that added up to 0, but I'm just not immediately seeing it. So what I'll do is I'll just (1, -1, 1, 1, 2, -1, and 3, -3, -1. And what I'm going to do, I'm going to row reduce the matrix that corresponds to these vectors squashed together. And figure out where the pivot's at, right? So I'm going to do that real. Okay, I wrote this and got that those were independent vectors. So I don't know if I copied the problem wrong when I typed up the homework. I don't know if I copied it wrong here. I don't know if I copied it wrong when I row reduced it or what. But I'm telling you, I'm just saying that, okay, part A is range trick 1 and part B is range trick 2, if you are up with the terminology in my class. And if I did make an error, come talk to me about it, and I'll work with you on how to do number 3. But for now, I'm probably just going to leave this as it is, because this is just more of our range tricks. You already kind of know how to do that. You seem like you're pretty good at it from what I've seen in class. So I'm going to let 3 be, and maybe I made an error working it. Maybe I made an error copying the problem from wherever I got it on the internet. But either way, I'm going to stop there. Anyway, number 4. Sometimes, always, never. Okay. Says if S is a subset of Rn, which is a finite number of vectors. So and this is going to be the case for Xn, right? No, okay, Xk. This is going to be the situation for the first 4 of them. And so K is less than or equal to N. This is a subset of Rn. So for A, if K is less than or equal to N, S can be linear independent, but it's not a guarantee, right? I could have, if say this was R3, and I had 2 vectors, I had 1, 0, 0, and 2, 0, 0, that would be linear dependent. But there would still be fewer vectors than dimension of the whole space. So I'm going to say that's sometimes. Okay. It could be independent, say IJK, right? That's always a really good example of a linear independent set in R3, IJ and K. So, but on one hand you've got IJ and K, still visible barely. And on the other hand, you've got 1, 0, 0, and 2, 0, 0. Okay, this one's independent, that one's dependent. Both of these are 3-dimensional vectors with the number of vectors less than or equal to the dimension of the space they live in. Okay, if K is greater than N, S is linear dependent. Yes. No, K is greater than N. I don't think that really looks like that doesn't really look like a Latin character, so I'm going to just try to. Maybe I'll just erase the whole thing. K is greater than N. This is always, because it said linear dependent. Okay, we proved this earlier in the class. This is pretty much equivalent to a homogeneous system with more variables than equations. It's got to have infinitely many solutions. It's 2 planes in space. Okay, they're either parallel or they run into each other, and in this case, they're going to run into each other. All right, because it's a homogeneous system, or equivalent to a homogeneous system. The investigation as to whether or not it's independent or dependent. All right, if K is greater than or equal to N, then S is a spanning set for Rn. Sometimes. But again, I could have a bunch of redundant vectors and it could not fill up. It could possibly not fill up the whole space. So that's sometimes on my phone. All right, lost my place, but I think it's in the middle of writing sometimes there. And then part D is K is less than N. Yes, okay. K less than N implies that S cannot span Rn. Okay. And that's true because the dimension of Rn is equal to N. So each basis will have N vectors in it. And a basis is a minimal spanning set. So if I don't have N vectors, I don't have a spanning set. So this is, S is not a spanning set for Rn. That's always true. That would have been a more interesting question if it said S is a spanning set for Rn, and then it would have been never. It seems like it's sometimes or always, always. So if B is a basis for Rn and W is a subspace, subset of B forms a basis for W. All right. So yeah, that's gonna be true, and that's always true. And I am not really coming up with a coherent response as to why, in terms of like the tools we have in this class. Let's see. Yeah, if you've got Rn, then you envision R3, and you've got a subspace for Rn, you're thinking like a plane or a line, then maybe not actually. Okay, yeah, I think this is. Oh, this one is tricky. I'm gonna say this one is sometimes true. Because it's saying, okay, B is a basis for Rn. Yeah, I got it. And W is going to need to be a plane that goes through the origin. But I'm going to say that there's no subset of this that forms a basis for W. Okay, let's say W equals the plane. Say Z equals X plus Y, maybe? Let's see. I think that will be okay, yeah. Probably should have paused the recording and investigated this before, but here we are. We're going to just try it. So if that's the case, then a basis would be, well, x1 and x2 are free to be whatever they want, and x3 is equal to the sum of them. So I think I have my basis for W, basis for R3. Basis for W, I think I'm going to have x3 is x1 and x2, so 1, 0, 1 for x1 and 0, 1, 1 for x2. Yeah, I don't think that I and J, that doesn't form a basis for W. And J and K, or, it has dimension 2, so it'd be some pair of I, J, and K would generate a basis for W. And I'm not seeing that as the case. So it's sometimes true, right? If we had say W was the YZ plane, then J and K would form a basis for that. But yeah, that's not always true. I think that what would be true always is that some linear combination of the basis vectors in B will form a basis for W, right? This, I can take these and linearly combine them to get these, but these themselves don't have to be basis vectors. Yeah, those are tough. All right, F. Yeah, if W is a subspace of Rn, W is a subset of Rn, and W is a subspace, and dimension of W equals N, then W equals Rn always. Okay, because it's basically equivalent to saying there are no three-dimensional subspaces of R3 besides R3, right? You can't have, like I said, you can't have a three-dimensional subspace of R3. It's going to be all of R3 or not dimension 3. Okay? So I think that's all I got to say about that one. Good set of problems. Sometimes always never is always interesting. Okay. So 5. Okay, W is a subspace of Rn, and V is pretty much W complement. It's like everything that's not in W. Question is V a subspace? I'm going to say V is not a subspace because it doesn't have the 0 vector in it. Now, if you had unioned this with the 0 vector and said it was everything that wasn't in W plus the 0 vector, that would be a more interesting question. And I think we talked about that in one of my classes today. But that's not the question that's asked, so that's not the question I'm going to answer. And I'm going to say, is V a subspace of Rn? No, the 0 vector is in W because W is a subspace, which means that the 0 vector is not in V, which means that V is not a subspace. All right, now number 6. This is a good problem on this set, I think. All right, this is a really good problem. This is where we're going to say find a matrix M, which is a 2x2 matrix with range of M equals null space of M. Okay. So what we're going to do is we're going to say, okay, if the range is equal to the null space, then the rank has to equal the nullity. And since it's a 2x2 matrix, that means the rank and the nullity are both 1. Okay. So that means that these need to both, well, they're equal, so they need to be the same one-dimensional subspace. Because of the rank nullity theorem. Okay. Then I'm thinking, well, I'm going to just need to decide what is going to be the range and the null space. So what I'm going to do is I'm going to say, well, I can do all sorts of things, but maybe I'll just decide that the x-axis is going to be the range and the null space. So since they're the same thing, both of these are going to be the null space. So this is the line y equals 0. Okay, maybe x2 equals 0. And just kind of go back and think about this like 3 blue. All right. And I kind of lost myself. I was giving somebody some papers. And so what's going on here? Okay, I've decided that the range and the null space need to both be this. Okay, so that means that if you think about what happens to, think about this like 3 blue and brown. The matrix that describes the transform is going to have 2 columns. And this is the, what happens when you take vector 1, 0 and run it through M. Well, 1, 0 is here on the x-axis, which is in the null space. So that needs to be 0, 0, because this is, right? And then over here, what's going to happen to 0, 1 is kind of the question under M. Okay. Well, 0, 1 had better go onto the y-axis. And, you know, I mean, we could put it anywhere on the y-axis that we wanted. I mean, on the x-axis, pardon me, that we wanted. So this one here, it just needs to go somewhere on the x-axis. So I need a vector that's on the x-axis. So anything where x is non-zero and y is 0. So maybe like 3 and 0. So I'll just say maybe that's 3, 0. But this could be anything I wanted. Okay? So this will be a matrix that fits that line. But I'm telling you, if you're tuning into this, I would encourage you to try any other line through the origin, the y-axis, the line y equals x, the line y equals 2x, some kind of line that goes through the origin, and try to replicate this yourself, and then come talk to me and see if you did it right. Okay, because this is a really, really good, meaty question. It's down to the really nitty-gritty of what we're doing here. Okay, so I need to go back to the problem set. And, oh, the intersection problems. Okay. I'm going to actually do number 8 first, because if you're just watching this with me and you've done neither of them, it actually makes more sense to work 8 and then go back and work 7. So for number 8, I'm going to say V and W are two-dimensional subspaces of R4. And so I'm going to say W and R4, V, subset of R4. Okay, the dimension of both of them is 2. And what is the possible dimensions of the subspace V intersect W? That's all the points that are in both V and W. And what I think is going to happen here is I'm going to get, I can't, like, you know, by intersect, you know, if this is A and that's B, I'm going to shade in the intersection. You know how that goes. You're familiar with the Venn diagram. You cannot see the A and B. That's A intersect B. Set of all points in both A and B. You can read that as and also. Anyway, you're not going to run two things into each other, take their intersection, and end up with a larger dimension than you started with. So I feel like 3, 4, not possible dimensions of the intersection. Instead, what I'm going to say is I feel like it could definitely be dimension 2. That could happen when V and W are the same plane. Okay. I think it's actually easiest to see, to go back to 0, and that would be if in the case where V equaled, how do I do this? Okay, the set of all vectors where V equals, let's say, you know, V1, V2, 0, 0, and W equaled the set of all vectors that were kind of the opposite. 0, 0, W1, W2. Yeah, that didn't go so well, but whatever. And the intersection is going to be where both of these things are true, and that would be where V1 equals 0 and V2 equals 0, W1 equals 0 and W2 equals 0. So V intersect with W is just the 0 vector. The 0 vector is a subspace. It has dimension 0, so that's the situation I'm talking about there. So then there's one more. I feel like dimension of V intersect W equals 1 is possible if, say, I just shifted this to W1 to up there. Okay, so I'll switch up the color and write this for you. Okay, this is if, oh man, I haven't written with this one in a while. All right. V is the set of all vectors, same, V1, V2, 0, 0. And W is the set of all vectors 0, W1, so that's where they're going to overlap if we just induced some overlap. Then we could say, well, the intersection, V intersect W, equals the set of all vectors, maybe I'll call it X this time, where V1 equals 0, where this is It can be anything because it doesn't have to be 0. This is 0, and the fourth one is 0. So 0, x, 0, 0, where x is any real number. A basis vector for that space would be 0, 1, 0, 0, so it has dimension 1. Okay. So my options are 0, 1, and 2. That's answer choice D on number 8. Okay. So number 7 is let W be 4-dimensional subspaces of a 7-dimensional vector space X. See what the answer is. Okay, it's not gonna be, I had a better explanation for this one last year. I don't remember what it was. And it's not on my key. I don't know why I would have done that. I think it was just like a discussion we had in class. But I remember discussing this problem at length last year in class. So V and W are 4-dimensional subspaces. So okay, they're subsets of a seven dimension subspace. I'm just gonna say it's R7, whatever. You can say it's X with dimension 7, but feels like R7. Anyway, dimension of W equals dimension of V equals 4. Okay. I'm proposing that, suppose, at their most minimal, where we try to kind of separate out the places where you had non-zero variables. Like I said, I'm gonna have 7 components, so that's kind of a lot. 4 dimensions, so I'll just do the first 4. V, I'm going to let be a so 0, 0, 0, V1, V2, V3, and V4. So I tried to separate them as much as possible, but still that 4th component is going to roam free, right? Because the intersection would have, okay, both of these conditions are true, right? And the condition for V is basically the first 3 components are 0. Condition for W is the last 3 components are 0. But the intersection is where the first 3 and the last 3 are 0. That still leaves that 4th one free to roam. So I know that the dimension of V intersect W is greater than or equal to 1. But I might also say it's less than or equal to 4 because I only really have 4 free variables to work with. Suppose they were all 4 in the same spot, then we would have, and same 4 down here, same 4 down here, then we would have a 4-dimensional intersection because they would probably do the same thing. Okay, but that's just what I'm going to say there, which is greater than 0, so 0 is the one that cannot be the dimension of the intersection. Okay. That was a good problem set. Thanks for watching.